let's pick up from where we left off. So we were talking about injection attacks, and we gave examples of SQL injection and command injection, both of which share this property that the vulnerable program is expecting some input from an untrusted user, and it's using that input to construct a string, and then the string is given to some kind of a command interpreter. Right? So in the first case, the interpreter was a SQL interpreter, or a database engine, and the second case, it's a shell. So the vulnerability is basically very similar, that this input is untrusted. It's coming from a remote user, and that user is specifically creating input that will cause some logic on the server side to get confused or tricked into doing something that the attacker wants. Okay, so script injection is, instead of dealing with SQL or shell, we could be dealing with many other scripting languages. And once again, if the vulnerable program takes some input, constructs a string from that input, and gives it to a command interpreter, then there's always a possibility of introducing a vulnerability there, and this is basically what script injection is. So let's look at cross-site scripting, which is essentially the injection of code into web pages, right? So I presume all of you know that web pages typically contain JavaScript. So if you, let's say, go to a bank, the bank will send you a web page, and that web page will typically have some scripts from the bank. Okay? And there's a security issue because this script that's coming from the bank has access to, say, things like your credentials. Right? So if you go to a bank, you probably are going to log in, and once you log in, you're able to do certain things, like maybe you're able to transfer money or wire money to some other account. So these are things that are possible because you have logged in. So these actions are under the control of the banking website, and the banking website allows you to do these things because you have authenticated yourself. But it is possible that if somehow an attacker, right, a third party that has nothing to do with the bank or you, if they are able to inject a script there, then the website thinks that this is actually their own script that they trust, and therefore they will allow it to do certain things that obviously they won't allow some random person to do. Right? So you can imagine, although this is not a real problem because banks are very careful about what actions they allow scripts to do. You don't. There is not a real threat that you will lose money because there's a JavaScript that's injected on your web page that transfers money to some Swiss bank account. Right? So that doesn't happen because there are additional checks in place. But in principle, this can happen because such an action would still be carried out by some request submitted from the bank's web page, and such a request could be submitted by a script running on the bank's web page. Okay, so later on when we talk about web security, then we will understand this point in more detail. But for now, just assume that any script running on the bank's web page is running with the privileges of the bank, and therefore, if that is malicious, then bad things could happen. So in this case, what happens is that the bank provides a feature for finding an ATM machine close to you. You provide you normally use it by providing a zip code, right? So there's a form field that says, give me the zip code of where you are, and you type it in, and under the covers, this is the field that you typed in is sent to the bank using a URL like this, right? So this is the base name of the URL that gives you essentially the page that you're accessing, and anything after the question mark is a bunch of parameters, right? So that page takes a few parameters, and the form field that you filled in is sent as a parameter. And on the receiving side, right, so we saw examples in the previous, so in this case, for instance, the send to list is nothing but a variable that contains one of these parameters, right? So there is it's not that there is some magic way of reading something into this. There is basically on the server side, the web application has to explicitly read a form field into different variables, okay, and that's what has happened here in the scene. But the point is that this variable that the attacker is using is coming through the same kind of mechanism as here, as a parameter on the URL. So what the server side program might simply say, hey, I'm going to echo that zip code and then say if there's an error. It's going to say, you typed in an invalid zip code, and so I can't find it. Okay. But of course, if the attacker typed in something like this, then it's possible, again, if the server side does not check or does not validate the input correctly, then it can simply think that this is actually a zip code that somebody typed in, and echo it right there. And the way HTML and JavaScript work is that this is taken as the URL of a script, and then the browser will go ahead and fetch this script from this address attacker.com, and then it's going to execute it. Right? So that way, attackers is getting executed, and this is what is called a cross-site scripting. And once again, the underlying problem is basically the same, which is that some untrusted input is not being checked for safety, and then it's being used as it is, and as a result, it ends up having an effect that the programmer did not anticipate or did not intend. So sometimes what happens is that there are validation checks, right? So as I said, so far the examples seem like the input validation check was completely missing. But you are more likely to find cases where the validation check is there, but it's somehow incomplete. Okay, so here is an example of an attack called directory traversal or path traversal, where the idea is that the attacker is able to examine files that's outside of the directory tree that they are supposed to see. Okay, so when you set up a web server, right? So you generally configure it so that with what is called a root directory that the users can visit. Right? So typically, the root directory for a web server will be some directory on the operating system like var www.html, right? So it's some directory that is deep inside the file system, which means that they should not be able to see what is in, let's say, /bin, right? A /bin directory or /live directory or /etc directory of your system, those should never be exposed to through the web server. Okay, that doesn't prevent the attackers from trying, because they know that if they say slash, that will just then take them directly to the root directory of the web server, which is, as I said, var www HTML, something like that, right? So, but they want to climb out of that, right? And then let's say they want to go all the way to the root, then they think maybe by putting some dots, they can climb out of the root directory and then go somewhere else, okay? And you may have, the programmer might have, realized that such an attack is possible, and then they may say, hey, I'm going to check if the file name contains dots, and if it contains dots, I'm going to just, let's see, what does it do? Yeah, so it basically says that if, this check basically, what it checks is whether the file name contains dot. If it contains dot, then this won't be null. This will tell you exactly where the dot is in that string, and so this part will not be executed. Right? Presumably, what will happen is that if dot exists, it will print an error and exit. Okay? The problem is what happens after that. So let's say there is no dot in the file name. The program then goes ahead and does what is called a URL decode. Okay, this is for dealing with special characters. So the special characters could be encoded using in hex like this, right? %2e is going to be treated as an ASCII code, and it's going to be replaced by the corresponding character. Okay, and what do you think %2e is?
Dot.
Right, it's dot. So you can imagine that if you have a very complex program where a number of such decoding operations are done, it's possible to have the check in the wrong place. Maybe some checks should be done after the decode, maybe some checks should be done before the decode, and you might get this wrong, and as a result, there may still be a way to get through and carry out the attack. So many years ago, right? You can see it's almost 15 years. So we looked at vulnerability reports and examined what are the different types of vulnerabilities that are being reported. Right? In 2006. So I took a subset of vulnerabilities to show in this pie chart. There are also a bunch of others that don't fit into any of these categories. Right? So sometimes these are all over the place. So there will be an error that says they used an incorrect encryption algorithm, or somebody omitted a check in some path. Okay, so these are sort of errors that are fairly specific to an application and not something that's broadly applicable across different applications. So what we did was we basically looked at these common vulnerabilities that occur frequently, and as you can see that in that year, roughly 2/3 of the vulnerabilities were reported related to these common vulnerabilities, and you can see that there was just a handful of those that pretty much covered. So if you look for those and try to avoid them, then you're already getting rid of like 2/3 of the possible vulnerabilities. So a few years later, right, 3 years later, we looked at this, and if you look at the thing, you'll see, okay, there are some changes, but not a whole lot. I mean, this SQL injection pie is still large, and cross-site scripting is still large. But you see a slight change here. So the fraction that falls into one of these simple classes is maybe more like 60% rather than 2/3. And then and we did this. The last time I did this is about it's still a while ago, 2012. Right? And now things have changed, right? So the interesting thing that you'll notice is that SQL injection reduced significantly. Right? It used to be like 1/3 of the pie. Now it's a small. And cross-site scripting hasn't changed, and memory errors sort of became bigger again. Right? And part of this is that so in 2005, 2006 timeframe, all of ASLR and all the memory protection mitigation, memory error mitigation mechanisms were put into place. So the attacks became a little bit more difficult. Okay, so and this continued for a while. But by 2012, people had figured out how to carry out attacks, carry out memory corruption exploits in spite of these defenses in place. And so you see that this share of the pie has expanded. The vertical bar is missing. I don't know what's going on, but I can tell you that by this time, only maybe 40% of okay, so it says that here. So half of it has come down to 50%. So these types of simple, clean, vulnerabilities comes down to about 50% of all the reported vulnerabilities, and the other half is more difficult because they are specific to an application and whatnot. So the interesting thing is that that all of these fall under the category of input validation errors. Right? So even in the case of the memory corruption exploits that we have talked about so far, it still is a case where there is some input coming from an untrusted source, and that input is not properly checked, and that's why it ends up, say, overriding a return address. Right? So that's not something that's supposed to happen. So these are all examples of input validation, and so one can think about, how do I deal with this type of errors in a generic way? And so the general picture is that there is some program that has some higher sensitivity access, and it also is accessed by some untrusted user, right? And it has to mediate these requests from an untrusted user and only allow sort of valid or legitimate requests to go through to the other side. So you can think of the sensitive access as maybe access files on the operating system, access command interpreters, database servers. Those are all sensitive accesses that this program has access to, and whereas the untrusted user can only access the program. They cannot directly access any of these sensitive services. So and with this general view, we can try to understand exactly what's going on in the case of this command injection attack that we have already looked at. Okay, so this is the same program, right? So the PHP program, so this is how you get a form field, right? So I showed you a form field that could be part of the URL that the browser submits, and that form field is extracted in PHP using this kind of a function call. Okay, that's _get, which is a special function which gets you this. And then it puts together, constructs a string using this variable that is obtained by parsing that form field, and then it uses PO. So these are all details that we already saw. I'm just showing you here. Here is where what the attacker provides, and then what we saw. Okay. So essentially, what's happening here is that the attacker uses the access, right? So the attacker somehow crafts an input, crafts a malicious input, and gives it over here. And their goal is to craft it in such a way that they will get access to something here that they are not supposed to have access to. So that's the goal. So there is a generic technique called taint tracking or taint analysis that can be used to keep track of what an attacker can control. Right? So taint means, so when you say something is tainted, that means it's somehow bad, right? So what you do is that because it comes from an untrusted source, you are going to taint it to say that there is something bad with it, and I'm going to follow the flow of this tainted data through my program, and then when that data is used, I'm going to look at it more carefully because I want to make sure that this untrusted data isn't used in an unsafe way. Okay? So the question is, what is unsafe, right? So this seems like it's difficult to figure out what is unsafe. Right? So it seems simple enough to follow the flow of tainted data. I have already done that by using a color there, right? So when it came, I put a red color here to say that this came from an untrusted source. Now, when the string is constructed, I know the part that came from the network, so it's just this part. So that part alone is red, and the rest of it is coming from the program itself. So I can use a color here, and then you can imagine that one can use some kind of metadata associated with the string to indicate that certain characters in the string are benign and certain others are